Okay, what's the cost here in big O? You start with O of n, right. Put it out, it's really O of n. How is that easy to detect? Well, you have a loop that executes in time. So it's O of n algorithm. Okay? How about this guy? Squared, right. Because if we were to put it out, it would become O of n squared. All right. How about this guy? Make sure I put these right.
No, it's not.
Aha, yeah, this one can be tricky.
Because I is less than n, but then it changes to j is less than n. So that, I guess because it's less than that, it should be n cubed, right? It'll always be less than n.
Okay, so I don't. So the, yeah, keep in mind that this time, even though beforehand we were, if you looked at the loops, it always went up to n. This time it's going up to a variable that depends on the previous execution of n. But if you're thinking about it on an average, it would still be basically n over 2. 2 over 2 is just 1/2. That's just a constant factor, so it kind of disappears. If you were to, you could go math this all out. You're going to come up with wow, the notation here is just not good. N cubed plus n squared plus n plus d. So it's actually an n cubed algorithm, which is really, hey, look, there's 3 for those. It usually becomes that easy. Do evaluate it, but yeah. Notice, you do not need to know the exact number of iterations to find the big O, because again, we are estimating, and this will be very, very useful. Okay. Lastly, all right, it can be somewhat hard. All right, what's this one? It can be, sure. Anyone? All right. Let's go do this one on the board real quick. I'm going to go ahead and math this one real fast because I think it's important that you understand why this is so important. Okay, so you have Hanoi. I'm going to call it T of n. What is T of n actually called? Well, it has some constant cost. All right, I don't care about that. And then what does it do afterwards? If the if statement's basically saying once n becomes 0, stop. Okay, that's great. So we know when we stop. But if n is greater than 0, let's say it's 3, what does it do? But what is it actually doing? It's calling itself, right? Right. So n minus 1 plus, does it call? What else does it do? It prints something out. Okay, we don't particularly care.
And
Calls itself again. All right. And I'm just going to say everything else takes 1, or big O of 1, just for sake of argument. Yes?
why is it T of n plus 1?
You didn't see that. Okay, you see what I did here? I simplified the cost down to 1 because it's really, if you take a lot of constant cost, it's O of 1. So I'm just going to call it 1 for now to make our lives easier. We could use C, but I'm going to stick with 1 to make our lives easier. Okay? Everyone see how I translated it from that to that? All right, let's go look at the board real quick. Okay. So really, T of n equals 2 times T of n minus 1 plus 1. Anyone know what that is? What's that in big O? Does anyone? Oh, man. All right, let's throw some numbers at it. Okay. Yeah, good guess. I'm glad it's good you're guessing. Let's throw some numbers at it. We're still up there. Great. We got n, and then we'll have t of n. So if it's, I don't know, 1, t of 0 is 0 by definition, because if you look back at the code, when n is 0, it exits. Yes? Oh, I thought I had a question. So these two are going to evaluate to 0. So it's 0 times 2, 0 plus 1. So the answer is 1. Great. How about 2? Well, it's going to call t minus n minus 1, which is 1. Multiply it by 2 plus 1, so that's 3. Let's put a 3 here. Again, t minus 1, which is 3. Hey, look, I'm glad we wrote these. 3, 6 plus 1 is 7. We'll put in 4. Hopefully you found the pattern. You take this, multiply it by 2, add 1. 5. Multiply by 2, add 1. Multiply by 2, add 1. And we'll do it one more time. This should be 127. Actually, I'll do it again, just for fun. 255. Anyone see what the pattern here?
Is that 2 to the power of n minus 1?
There we go. Yes? Did y'all see that? So the question is, or actually, let me write this. T to the n equals 2 to the n minus 1. Well, anyone know how you prove this? Anyone in discrete math? Has anyone taken discrete math? Okay. You're in it right now? Okay. I'm going to do this because a lot of students, when Dawson explains we're going to learn induction, a lot of students have given her some grief, which is not cool. Not good, guys. I'm going to show you why. You do a proof by induction. What's proof by induction? All right, let's prove it for the base case, right? First, 1, show t of 1 equals 2 to the 1 minus 1. All right, well, t of 1 is, of course, 1, which equals 2 minus 1. So 1 equals 1. Everyone good? All right. So that proves the formula works for the first one, right? Okay. Proof by induction. 2. Next, assume t of n equals 2 to the n minus 1. Show t of n plus 1 equals 2 to the n plus 1 minus 1. We assume the previous is correct. We've already assumed this. So assume that at each step moving forward, the formula is going to hold in general. Okay? All right. Okay. So we want to prove that t of n plus 1 is that. All right. So t of n plus 1, well, we have this formula up here, which is equal to 2 of t of n plus 1. Well, t of n, that's our assumption, right? Good. So we can say that this equals 2 times 2 to the n. What do we got? 2 to the n minus 1 plus 1, which is equal to basically 2 to the n plus 1 minus 2 plus 1, which equals to 2 to the n plus 1 minus 1. And is that what we were trying to prove? Yes, it is. We get to the little box, or you can do your happy face, or whatever you like. Okay. This is a very, very simple one, of course. But do you see why the proof's important? So is this a good algorithm to run? No. Don't run this algorithm. All right. Oh, any questions on this? You'll learn this way more in depth in discrete math, but hopefully you'll appreciate discrete math a little more. Turns out it's 2 to the n. Another way to think of this is for every n, we make 2 to the n minus 1 calls, which eventually will result into some 2 to the n. If we called ourselves 3 times, what would you expect this to be? 3 to the n. Hopefully hopefully you're starting to see a couple patterns here. All right. Okay. Let's go ahead and pause.